Welcome! In this session, we'll tackle an exciting problem titled Maximize the Value of the Gift Cards. Together, we'll explore different approaches to solving this problem, including a brute force method. Let's dive in and unlock the optimal solution step by step. To solve the problem of maximizing the gift card value, we first consider a brute force approach. This method is straightforward in concept. It involves exploring all possible ways to distribute the gift cards to maximize the total value while meeting the constraints. For each subset of gift cards, we calculate the total value and check if it satisfies the rules. While this guarantees correctness, the sheer number of subsets makes this approach computationally expensive. With n gift cards, there are 2 n possible subsets to evaluate, resulting in an exponential time complexity. Clearly, this method is impractical for large inputs. Instead, we turn to a more efficient solution using dynamic programming. By defining dp, j, as the maximum value we can achieve with a budget of j, we can break the problem into smaller overlapping subproblems. For each gift card, we decide whether to include or exclude it from the current budget. The recurrence relation captures this decision. dp, j, equals the maximum of its current value or the value obtained by including the card, as long as the budget j allows. We start with the base case, dp, 0, equals 0, since no cards yield no value. The final answer is then the maximum value in the dp array for the given budget. Another approach to consider is a greedy algorithm. Here, we sort the gift cards in descending order of value and attempt to assign the highest value cards first. This method is computationally efficient, as sorting takes n log n, and the assignment is straightforward. However, the greedy approach does not guarantee the optimal solution. This is because it does not account for how smaller combinations of cards might fit better within the budget, making it unsuitable for problems with combinatorial constraints like this one. Instead, we choose the dynamic programming approach as the most appropriate strategy. It excels because it leverages the problem's optimal substructure. Smaller subproblems can be solved independently and combined to solve the larger problem. The time complexity of n budget is significantly better than the brute force method's exponential complexity, and unlike the greedy method, dp guarantees the correct, optimal solution. While brute force is infeasible and greedy is unreliable, dynamic programming strikes the perfect balance, making it the best choice for this problem. The breakthrough insight for this problem is recognizing its similarity to the classic knapsack problem. Both involve maximizing value while staying within a given budget or capacity. This realization allows us to adapt the well-studied dynamic programming solution for knapsack problems to our scenario. The implementation uses a one-dimensional array to save space, where dp, j, represents the maximum value achievable with a budget j. During computation, the dp array is updated in reverse order to prevent overwriting states that are still needed for future calculations. This approach ensures that the solution is not only time-efficient but also space-efficient, making it practical for larger inputs. By leveraging this analogy and optimizing the dp implementation, we achieve a robust and scalable solution to maximize the value of the gift cards. To solve the problem of maximizing the value of gift cards under certain constraints, we start by understanding the inputs and rules. Imagine we have a list of gift card values, represented as an array, such as cards equals v1, v2, vn. Along with this, we have constraints to consider, such as the maximum number of cards each person can receive or the allowable value range for any individual. The first step is to parse this input and extract the constraints so that we can structure our solution appropriately. Next, we generate all possible subsets of the gift cards. This can be achieved either recursively or iteratively, and it involves exploring all combinations of the cards. Since there are 2 n subsets for n cards, this step can become computationally expensive as the number of cards increases. For each subset, we calculate the total value and the number of cards it contains. Once we have these subsets, the next step is to filter them. We discard any subsets that violate the given constraints, such as exceeding the maximum number of cards per person or falling outside the value range. Only subsets that meet all criteria are retained for further processing. After filtering the valid subsets, the next challenge is distributing these subsets among individuals. For each valid subset, we assign it to one person and then recursively repeat the process for the remaining cards and individuals. It's important to keep track of which subsets have already been used to ensure that no subset is duplicated in the distribution. Once we have a distribution, we calculate the total value for that arrangement by summing the values of the gift cards assigned to all individuals. The goal is to track the maximum total value observed across all possible distributions. Finally, we output the distribution that yields the highest total value, along with the value itself. This process highlights some key insights. Generating all subsets has exponential complexity, which makes it computationally expensive for large input sizes. However, by filtering out invalid subsets early in the process, we can significantly reduce the number of subsets we need to consider, thus improving efficiency. Additionally, distributing the subsets recursively allows us to break the problem into smaller, more manageable subproblems, making the solution easier to conceptualize and implement. To implement this algorithm effectively, we rely on specific data structures. A list is used to store the gift card values, the subsets, and the distributions. A set is particularly useful for tracking used subsets, ensuring that no duplicate assignments occur. Finally, a dictionary helps map individuals to their assigned gift cards during the distribution process, making it easier to track and retrieve assignments. There are also several edge cases to consider. For instance, if no gift cards are provided, the result should be a total value of 0 with an empty distribution. If constraints are so tight that no valid distribution is possible, the algorithm must handle this gracefully, possibly returning an empty output. When gift cards have equal values, the algorithm should ensure that duplicates are handled correctly without introducing bias. Additionally, for large input sizes, it becomes critical to optimize the subset generation process, as the brute force approach may become impractical. To address these challenges, we can explore optimizations. Dynamic programming can replace the brute force approach for subset generation, enabling us to solve the subset sum problem more efficiently. A greedy heuristic can also be employed to prioritize assigning the largest available card values first, which helps meet constraints while reducing computational overhead. These techniques can significantly enhance the algorithm's efficiency and scalability. The code implements a solution to maximize the value of selected gift cards given certain constraints. Here's a breakdown of the implementation. 1. Imports. The itertools.combinations import is included, but in used in this solution, it can be removed for clarity. The max function is used to determine the optimal value at each step. 2. Sorting. The gift card values are sorted in descending order to prioritize higher value cards during selection. This ensures an efficient computation when using the dynamic programming table. 3. Dynamic programming table. The DP table is instantiated with dimensions n+1 x max _cards plus 1. Each cell DP, I, j, represents the maximum value achievable using the first I cards and selecting up to j cards. 4. Transition logic. The nested loop iterates over the cards and the selection count. For each card, the algorithm decides whether to include it in the selection. Exclude the card, the value remains as dp, I1, j. Include the card, the value becomes dp, I1, j1, plus gift _cards, I1, if a card is still allowed to be selected. The maximum of these two values is stored in dp, I, j. 5. Result. The bottom right cell of the DP table, DP, n, max _cards, holds the maximum value achievable under the given constraints. 6th example. In the example, 5, 3, 8, 6, 2 represents the gift cards, and 3 is the maximum number of cards that can be selected. The function calculates the maximum value achievable by selecting up to 3 cards, which is printed as the result. This approach ensures that all combinations of selections are considered efficiently, with a time complexity of O, n * max _cards, where n is the number of gift cards. This makes the solution suitable for moderate input sizes, such as those typically encountered in competitive programming scenarios. Here, we begin by importing necessary libraries and defining our solution class. The core method, maximize the value, takes 2 inputs, an array of integers representing the gift card values and an integer max cards, which is the maximum number of cards we can select. Inside the method, we start by determining the length of the gift cards array and sorting it in ascending order. Since we aim to maximize the value, we then reverse the array to ensure it is sorted in descending order. For this, we call the helper method reverse array. Next, we initialize a 2D dynamic programming table, DP, where DP, I, J, will store the maximum value achievable using the first I cards and selecting up to J cards. The dimensions of the table are based on the number of cards and the maximum cards allowed. After initializing, we iterate through each card using a nested loop. The outer loop runs through all available cards, and the inner loop processes the possible card selections. Inside, we have two choices: skip the current card, retaining the previous maximum value, or include the card, updating the maximum value based on the remaining capacity. The result is stored in DP, N, max cards, which is returned at the end. The reverse array method, defined next, inverts the order of the gift cards array using a two-pointer approach. This ensures the array is sorted in descending order after being initially sorted in ascending order. The main method demonstrates how to use the solution class. We create an instance of the solution class and define a sample input where the gift card values are 5, 3, 8, 6, 2, and the maximum number of cards we can pick is 3. By calling maximize the value with these inputs, we compute the maximum value that can be achieved under the given constraints. Finally, the result is printed to the console. In this example, the output will show the maximum value of gift cards that can be selected, allowing us to verify the correctness of our implementation. To solve this problem, we start with a simple example where the input gift cards array is 5, 3, 8, 6, 2, and the maximum number of cards we can select is 3. The first step in our approach is to sort the gift cards in descending order, which gives us 8, 6, 5, 3, 2. Sorting ensures that we consider the most valuable cards first. Next, we initialize a 2D dynamic programming table, or DP array, with dimensions n+1 x max underscore cards plus 1, in this case, a 6x4 table filled with zeros. The DP, I, J, entry will represent the maximum sum we can achieve using the first I cards while selecting up to J cards. With the setup complete, we move on to iterating through the gift cards to fill in the DP table. We begin processing each card to fill the DP table. For the first card, which has a value of 8, we update the table as follows: DP 1, 1 becomes 8, as we can only select this card. Similarly, DP 1, 2, and DP 1, 3 also become 8, because selecting only one card gives the same result regardless of the maximum limit. After this step, the DP table reflects these updates. Next, for the second card, which has a value of 6, we calculate the maximum possible values for each limit of cards. For example, DP 2, 1 remains 8, as it's better to keep the first card. For DP 2, 2, we add the second card to achieve a total value of 14, and for DP 2, 3, the value remains 14, as adding more cards hasn't improved the sum yet. These updates ensure that the table tracks the optimal choices up to this point. Continuing this process, we handle the remaining cards one by one. For the third card, which has a value of 5, we update the table to reflect the best possible sums for each card limit. Similarly, we incorporate the values of the fourth and fifth cards, which are 3 and 2, respectively. After processing all entries, the final value in DP 5, 3, representing the maximum value achievable using all 5 cards while selecting up to 3 cards, is 19. This completes the first example. Now, let's consider an edge case where the number of cards is fewer than the maximum allowed. In the second example, we have only 2 cards, 4, 7, and the maximum number of cards allowed to select is 3. After sorting the cards in descending order, we get 7, 4. The DP table is initialized as a 3x4 matrix filled with zeros. Since we only have 2 cards, we iterate through them to update the table. For the first card, which has a value of 7, we update the relevant entries in the DP table. Then, for the second card, with a value of 4, we make further updates. Ultimately, the best value we can achieve is 11, which is stored in DP 2, 2. Here, the result is limited by the fact that we only have 2 cards to work with, even though the maximum allowed is 3. Finally, let's look at a case where we can select all the cards. In the third example, the cards are 10, 20, 30, and the maximum number of cards allowed is 3. Since the array is already sorted in descending order, no rearrangement is needed. The DP table, initialized as a 4x4 matrix, is updated progressively as each card is considered. With 3 cards and a maximum of 3 selections, we can include all the cards, resulting in a total value of 60, stored in DP 3. From these examples, several key observations emerge. First, sorting ensures that we process the most valuable cards first, which maximizes the sum. Second, the DP table systematically tracks the maximum value achievable for each subset of cards in each card limit. Finally, deciding to skip or include a card depends on whether its inclusion improves the total value, which is determined by our iterative updates to the DP table. In the provided solution, we use dynamic programming to maximize the value of the gift cards. To analyze the time complexity, we start by considering the sorting step. Sorting the gift cards in descending order is performed using the sort function, which has a time complexity of O, n log n, where n represents the number of gift cards. Next, we initialize the dynamic programming DP table. The table has dimensions n plus 1 is x max underscore cards plus 1, meaning we allocate space for all possible numbers of cards and all gift cards. Initializing and filling this DP table with zeros involves O, n asterisk max underscore cards, time. Lastly, we consider the process of filling the DP table. The outer loop iterates through each of the n gift cards, while the inner loop iterates through all possible values up to max underscore cards. For each combination, we perform constant time operations like comparisons and arithmetic. Combining these, filling the DP table requires O, n asterisk max underscore cards, time. Overall, the time complexity is determined by the sorting step and the DP computation, resulting in a total time complexity of O, n log n plus n asterisk max underscore cards. The combined time complexity, O, n log n plus n asterisk max underscore cards, is dominated by the n asterisk max underscore cards term when max underscore cards is sufficiently large. Now, for the space complexity. The DP table requires memory proportional to its dimensions, which is n plus 1 is x max underscore cards plus 1. This results in a space complexity of O, n asterisk max underscore cards. Additionally, the sorted gift underscore cards list consumes O, n, space, while loop variables and other temporary values use O, 1, space. Since the DP table is the dominant factor, the total space complexity is O, n asterisk max underscore cards. This highlights that both time and space complexity scale with the size of the input, particularly the number of gift cards and the maximum number of cards we can select. Analyzing the best, average, and worst-case scenarios, we find that the time and space complexity remain consistent across all cases. Regardless of the input values, the algorithm always performs the same steps, sorting the gift cards and filling the DP table, making its computational requirements purely dependent on n and max underscore cards. Comparing this to a brute force approach, where all combinations of gift cards of size max underscore cards are generated and evaluated, we see a stark difference in efficiency. The brute force approach has exponential complexity, O, n caret max underscore cards, due to the combinatorial explosion of possibilities, making it impractical for larger inputs. In contrast, the dynamic programming solution avoids redundant calculations by leveraging overlapping subproblems, achieving a far more manageable time complexity of O, n asterisk max underscore cards. This makes dynamic programming an optimal choice for solving this problem efficiently. In conclusion, the dynamic programming approach offers a significant improvement in efficiency and scalability compared to the brute force method. With a time complexity of O, n log n plus n asterisk max underscore cards, and a space complexity of O, n asterisk max underscore cards, it is well suited for moderately large values of n and max underscore cards. However, for extremely large inputs, memory constraints may arise due to the size of the DP table. In such cases, further optimizations, such as reducing the DP table to a 1D array, can be considered to minimize space usage while preserving the algorithm's efficiency. Overall, this solution strikes a good balance between computational feasibility and simplicity, making it a robust choice for this problem. When solving this problem, there are a few common mistakes to watch out for. First, failing to handle edge cases can lead to crashes or incorrect results. For example, if the input array is empty, if there are duplicate gift card values, or if the problem constraints require a minimum total value per person that simply can't be satisfied, your solution needs to account for these scenarios. To address this, it's crucial to validate your inputs thoroughly and include checks for boundary conditions in your code. Another frequent mistake is the incorrect use of greedy algorithms. While it might seem intuitive to always assign the highest value gift card first, this approach can lead to suboptimal distributions over time if the problem doesn't satisfy the greedy choice property. In such cases, alternative approaches like dynamic programming or exhaustive search might be necessary. Lastly, a brute force implementation that explores all possible subsets without pruning can become computationally infeasible as the input size grows. Techniques like memoization, backtracking, or applying early termination conditions can help reduce the search space and improve efficiency. It's also important to avoid misunderstanding the constraints. For example, the requirement that each person must receive at least one gift card or the need to maximize the minimum total value across individuals can be easily overlooked or misinterpreted. To prevent this, take the time to carefully read the problem statement and translate the constraints into clear, logical implementation rules. During testing, double-check that your solution adheres to these constraints. Another common pitfall is overcomplicating the solution. Adding unnecessary complexity, such as using advanced data structures when simpler ones would suffice, can make the code harder to debug and slower to run. Instead, aim for clarity and simplicity in your implementation, and only optimize further once you've confirmed the correctness of your solution. For interview scenarios, there are some key strategies you can use to perform well. Start by identifying problem patterns early. Many problems involving the distribution of values can be mapped to well-known techniques like binary search, dynamic programming, or backtracking. Recognizing these patterns quickly will save valuable time. Also, make sure to clearly communicate your assumptions to the interviewer. For example, if you're dealing with inputs that might not satisfy the constraints, explain how your solution will handle those cases. Testing incrementally is another important step. Begin with small and manageable cases to catch boundary errors early before scaling up to larger inputs. Finally, always analyze the time complexity of your approach. Be prepared to discuss potential trade-offs, especially if you're using a brute force or dynamic programming solution. Interviewers often appreciate when candidates can optimize their initial solution. For additional practice, you can explore related problems such as partition to k equals some subsets, split array largest sum, capacity to ship packages within D-days, and Coco eating bananas, which share similar concepts. There are several alternative approaches you can consider for solving this type of problem. Backtracking with pruning is a systematic way to explore all possible distributions while eliminating unviable paths early. While this method guarantees correctness, it can become computationally expensive for larger inputs unless aggressive pruning is applied. Another approach is dynamic programming, where you define a DP state that represents the current distribution and iteratively build upon it. This is generally more efficient than backtracking but can require significant memory and may be complex to implement, especially when the state space is large. Binary search on the result is another powerful technique for problems where you need to maximize a minimum value. By combining binary search with a feasibility check, you can significantly reduce the solution space, though this requires a carefully designed feasibility function. Finally, in some variations, a greedy approach might work if the problem satisfies the greedy choice property. For instance, you could assign the largest available gift card to the person with the current lowest total. However, greedy methods can fail to produce the optimal solution if earlier decisions impact the global outcome, so use this approach cautiously. Great job! We've successfully walked through the problem, maximized the value of the gift cards, and explored a brute force approach. Remember, every problem is an opportunity to grow your problem-solving skills. Keep practicing, and we'll see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!